Okay, welcome back. It's Thursday night. Sorry it's so late. I'm going to record some videos now going over the homework on Rolle's theorem and the mean value theorem. And I apologize once again for that video being kind of so-so. Learning about it. Anyway, let's go over it, and hopefully in the going over of the homework we can get some kind of understanding of it better if we need to. So here we go, number one. Number one said, well, it gave you a function, f of x equals 1 minus absolute value x minus 1, and actually even gave you a picture of this function. And well, we don't even need the picture, we know how to graph this. This is the absolute value function, moved 1 to the right, flipped upside down, and moved over 1. So yeah, 1 to the right, upside down, moved over 1. So when you plug in 1 here, you'll get, you'll get 1. Anyway, it looks like this, right? I think I did that right. Moved over 1, upside down, moved over 1, yeah. Okay, and now the question is, explain why Rolle's theorem does not apply to the function even though there exist a and b such that f of a equals f of b. Okay, so this is a little bit awkward. They specifically are addressing, it's a little bit vague, but I guess they're specifically addressing this function on the interval 0, 2. So consider this function on the closed interval 0, 2, and you might be tempted to apply Rolle's theorem in this situation, because after all, f of 0 is equal to f of 2, which is 0. And what does Rolle's theorem say? It says what goes up must come down, and if you start, and this is what we did on the video and in the book, if you have a function which is continuous and differentiable, and the y value of that function is the same at the beginning and end of the interval, then there must exist a point somewhere on the interval in which the derivative is 0. That's the content of Rolle's theorem. So the simplest answer to this problem is, yeah, Rolle's theorem is just not applicable here. So I'll just write that. Rolle's theorem does not apply to this function f on the interval 0, 2 for the simple reason that this function is not differentiable on this interval. And in fact, you can see that we've done problems like this before, that f prime of 1 does not exist because this is sharp. This function is sharp at f prime of 1. And in fact, it's just true that there is nowhere on this interval for which the derivative is 0. And so, in fact, there does not exist a c on the interval 0, 2 such that f prime of c is 0. So it's wrong to apply Rolle's theorem in this situation, and if you tried to, you would produce a false conclusion that somewhere the derivative is 0, and in fact there's nowhere on this interval at which the function is 0. The derivative is 1 on the interval 0, 1, and it's negative 1 on the interval 1, 2. Okay, so kind of maybe a weird place to start, but there it is. And I think number 4 is it's just kind of more of the same. Okay, so they give us some disgusting function like f of x equals the square root of 2 minus x to the 2/3, and all of that is cubed. Okay, and we're supposed to be looking on this on the interval negative 1, 1. Well, here they don't give us a picture, and maybe we just don't even want one. Let's see if Rolle's theorem is applicable. Hint, it's not applicable. The very problem says show that it isn't. Well, I will rewrite this function in a kind of a derivative-friendly form. This is really like 2 minus x to the 2/3, all to the 3/2. And well, maybe that doesn't look so scary at the moment, but I know that x to the 2/3 is like the bird, which is sharp, so it's upside down bird. And I think this is not going to make it any better. If you just take the derivative of this function kind of blindly using the chain rule, then we see that the answer is 3/2, 2 minus x to the 2/3 to the 1/2 back inside for the derivative of 2 minus x to the 2/3, which is negative 2/3 x to the negative 1/3. So this is just kind of some chain rule practice now. Let me make sure I did that right. I think I did. Back inside here, yeah. Okay, and so what is this big mess? These cancel, and what we end up with is something like negative root 2 minus x to the 2/3 over the cube root of x. And I think writing the function in this form makes it pretty clear that f prime of 0 does not exist. And so since f prime of 0 does not exist, and 0 is certainly on the interval negative 1, 1, then we can't apply Rolle's theorem here because this function is not differentiable on this interval. Okay, so and is there anywhere on this interval in which the derivative is 0? Yeah, I don't think so, right? Because, yeah, I don't think so. Because in order for this derivative to be 0, that numerator would have to be 0, and in order for that numerator to be 0, we would need x to the 2/3 to be 2 somewhere, and that would mean, by raising both sides to the 3/2, that x would have to be 2 to the 3/2. But 2 to the 3/2 is something bigger than 1. And so, in fact, there are no solutions to this. There are no times on the interval negative 1, 1 at which this function has derivative 0. And why would you be tempted to apply Rolle's theorem? Well, you would be tempted to apply Rolle's theorem perhaps because, I failed to mention this, that f of 1, if you plug in 1, you get 1 to the 2/3 is just 1, so that's 2 minus 1 is 1, and so you just get 1. And if you plug in negative 1, you also just get 1. This is an even function. So despite the fact that it has the same y value at the beginning and the end, Rolle's theorem is not applicable. Alright, it's kind of a strange way to start the homework with some examples in which you can't apply Rolle's theorem. Hopefully we can actually talk about some problems where you can apply Rolle's theorem. And, well, here we go. This is number 7. Number 7 says, find the two x-intercepts of the function and show that the derivative is 0 at some point between the two x-intercepts. Okay, so this is f of x equals x root x plus 4. And it says find the x-intercepts. In other words, when is this function 0? Well, I think it's pretty obvious that f of 0 is 0, and also that f of negative 4 is 0. And so, what we're now going to do is apply Rolle's theorem to f on the interval negative 4, 0. And Rolle's theorem says that if you have a function and it has the same y value, in this case that y value is 0, at the beginning and end of the interval, then there must be somewhere where the derivative is 0. And in fact, we can just find it. That's what they want you to do, I believe. Show that the derivative is 0 at some point between the two x-intercepts. They don't specifically say find the place where the derivative is 0. So that is slightly vague as to whether they want you to actually find the point, or whether you're just supposed to say, Rolle's theorem, we're done. Let me just see maybe what the book does. Yeah, they do find it, so let's find it. It's good practice anyway. This is the kind of thing that we got good at last week, hopefully, but it's actually still quite hard. So what is this function? This function is x root x plus 4. So we're going to rewrite this in derivative-friendly form as x plus 4 to the 1/2. Okay, and now we're going to differentiate. And when we differentiate, we get the derivative of the first times the second, so that's x plus 4 to the 1/2 plus the first times the derivative of the second, and that will be 1/2 x plus 4 to the negative 1/2 back inside for the derivative of x plus 4, which is just 1. Okay, and here we get an opportunity to practice our new sort of advanced algebra technique, which is when it comes to simplifying this derivative, the thing to do is to factor out x plus 4 to the negative 1/2. And why? Because both of these terms have an x plus 4 in them, and so we want to take out the one with the lower power. And if we're being very smooth, we can also factor out the 1/2 at the same time, because it's nice to get the fractions out of the way. Okay, so when we're doing that, since we factored out a 1/2, but there was no 1/2 here, we need to put in a 2, and then we need to put in some number of x plus 4s. Well, what does this exponent have to be in order for this to multiply out correctly? Well, something to the negative 1/2 times something to the 1 is something to the 1/2, so that has to be 1. And then here we have just plus x. We check out the 1/2. And I think when you, okay, I'm very good at this by now, so this feels natural to me. But while you are learning this, I think it's a really good habit to just multiply everything back through, really whenever you factor, but especially with this kind of new technique, and just confirm to yourself, yeah, this is all working out. All right, why is this so good? This is so good because now I can very easily simplify what's going on here. And what I have is 2x plus 8 plus another x. So this is 3x plus 8 all over 2 root x plus 4. And that is a very nice form to have your derivative in. You can see precisely when the derivative is 0, when it doesn't exist, etc. And well, the answer is that this derivative will be 0, which was the goal, when the numerator is 0, which happens at negative 8/3. So f of negative 8/3 is in fact 0, and negative 8/3 is a little bit less than negative 3, so it's on the interval. It's on the interval negative 4, 0, and so that just is the answer. So on the one hand, Rolle's theorem asserts that this function will be differentiable. We'll have derivative 0 somewhere on this interval, and in fact we just found the point. What does this graph look like? Let's see. Well, it will be negative until 0 and then positive thereafter. So I guess this is going to look something like that, is roughly what this graph looks like. You can't plug anything less than negative 4 into this function, otherwise it will be undefined. When x is really big, like 1,000,000, it's going to look kind of like x to the 2/3, and it's going to be negative until 0 and positive thereafter. Okay, 3 down, many to go. Number 19. Let's see if it's possible to squeeze one more problem in here. Number 19, I think, is it the same directions? No, slightly different. Here it says, well, first it gives us a function. Let's write the function down. The function is x squared minus 2x times e to the x. And specifically, we are looking at this function on the interval 0, 2. Okay, here are the directions. Determine whether Rolle's theorem can be applied to f on the particular interval. If Rolle's theorem can be applied, find all. Okay, so it's basically the same thing. Is Rolle's theorem applicable here? I bet it is. Let's see, if I just plug in 0, then indeed I get 0. And if I plug in 2, they supply me with this closed interval. If I plug in 2, then I get 4 minus 4 is 0, so I also get 0. So indeed, this function begins and ends at the same y value, and also, crucially, this function is differentiable because it's just a product of two differentiable functions, a polynomial and an exponential function. Okay, so we can apply Rolle's theorem to this function on this interval, and so there must exist a c on the interval 0, 2, such that f prime of c is 0. I guess this is like open. Somewhere on the inside, this derivative must be 0. And let's now find the place where the derivative is 0. Okay, well, we'll just differentiate this function, I guess. So I think I can squeeze this in. I have to use the product rule. So the derivative of the first is 2x minus 2 times the second, which is e to the x, plus the first times the derivative of the second. So that's x squared minus 2x times the derivative of e to the x, which is just e to the x. Okay, so I have now something where I can factor out e to the x, and I'm left with a polynomial behind, let me just double check this, derivative of the first, 2x minus 2, yeah, okay, so I guess the 2x's cancel, yeah, and I'm just left with x squared minus 2. Okay, so that's kind of nice. So this is a nice form to have the derivative in, because we can see precisely when this derivative will be 0. So I now set this derivative equal to 0. Well, e to the x is never 0 because it's always positive, and so the only time it's going to happen is when x squared minus 2 is 0, and that happens when x is plus or minus root 2. So root 2 and negative root 2. But the answer to this question is find the value of c guaranteed by Rolle's theorem. Rolle's theorem guarantees you a point on the interval 0, 2 where the derivative is 0. So both of these points are points where the derivative is 0, but only one of them is relevant because only root 2 is on the interval 0, 2. So this is, though a solution to the equation, is not it's not our point of interest. And so Rolle's theorem guarantees us a place with the derivative of 0, and indeed that place is when c is root 2 on this interval. Okay, good. More, just take 2 minutes here and erase this. This is the first time I'm recording a video at night, so baby's sleeping in the other room, and the light is going to be kind of weird. I hope it's visible. Okay, 44. Oh man, I assigned a bunch of evens now, so I guess it is good that I'm going over this problem. What is number 44? Number 44 is skipping ahead to the mean value theorem. Yeah, which is sort of the real subject of this section. Rolle's theorem we spent a lot of time talking about and sort of proving, but in some ways Rolle's theorem is most important as a tool to proving the mean value theorem, which is the one we're going to use, sort of more often. So what does it say? It says determine whether the mean value theorem is applicable to the function on the given interval, and then find the values of c. Okay, so let's do it. We have a function, f of x equals x squared minus x squared minus x minus 2, and we're given this function on the interval -1, 1. All right, well this is a polynomial, and polynomials are functions that we're very comfortable with, so this will be good. Maybe we can make a graph of this function if it factors, and I think it does, because that's x minus 2, x plus 1. What does this function look like? Well, it's just polynomial, and it has roots at -1, 0, and 2, and it's going to be, it's going to be just a cubic, so it's just going to look like that. Okay, so this is even just pre-calc C. And now they say, and maybe we should actually, on the interval -1, what happens when I plug in 1 here? I get 1 minus 1 minus 2 times 1. So this is in fact -2. So maybe it's good to draw this kind of accurately. And okay, something like that, although I'm not sure that's a root or not. So let me just do something like that. I don't know. But okay, so here's this point, 1 comma -2. Hope I did that correctly. 1, 2, -1, yeah. And then, of course, I'm plugging this number 1 in because 1 is the right endpoint of my interval, and when I plug in -1, I get 0. So that's -1, 0. Okay, and what should we be saying about this function? Well, on the interval -1, 0, this function changes. And sort of by how much does it change? Well, it goes down 1 and over 2. And so it's not a good picture, but maybe I just don't, maybe I don't draw the triangle. Maybe I'll just draw the change. So here is the one point and here's the other point. And so the change in this function is down to sorry, it's down 2 over 2. So this slope is 1, actually. And, well, this is just what the mean value theorem says, right? It says, the mean value theorem says that, if f is continuous and differentiable, then there exists a point C on the interval AB such that the derivative at C is equal to f of b minus f of a over b minus a. In other words, calculate for any given function in any given interval the change in that function, divide by the sort of time it took to produce that change, and what you get is the average rate of change. And the mean value theorem says that there must exist a point somewhere on the interval where the instantaneous rate of change equals the average rate of change. And so what we need to calculate is the average rate of change. And, well, okay, we sort of did it already, right? This is like f of 1 minus f of negative 1. That's the change in the function on the interval negative 1, 1. Over 1 minus negative 1. And, all right, we already calculated this based on just looking at it and talking about it, but I'll do it again. F of 1 we said is negative 2, and f of negative 1 is 0, so that's negative 2 over 2, and so this is negative 1. So we have to get comfortable with this kind of language. The average rate of change on f is negative 1, which is to say, on average, this function is changing at the rate negative 1. Okay, and negative 1 is in fact the slope of this purple line. I think colors are going to come out even worse than usual here, but that purple line connecting those two dots has slope negative 1, and so what we want to see is where on the interval negative 1, 1 is the instantaneous rate of change equal to negative 1. And that's exactly what the mean value theorem guarantees. That if the overall change, if the overall rate of change is negative 1, then somewhere on the interval, the instantaneous rate of change is negative 1. This is the content of the mean value theorem. Okay, and so, well, we can just do it now by doing some calculus. So first of all, I think it makes most sense to just multiply this out. If I multiply this out, I get x cubed minus x squared minus 2x is the function written out in kind of standard polynomial form. So now we take the derivative. We get 3x squared minus 2x minus 2. So that's the derivative. And what I now want to do is set this derivative equal to negative 1. Because I want to know when, if ever, on the interval negative 1 to 1, is the derivative equal to negative 1, which is the average rate of change of the function on this interval. Okay, and now we just have a quadratic to solve. So minus 2x minus 1. And does this just factor? I guess it just does, right? 3x, 1, x, 1. I'm hoping it factors. 3x squared, yeah, minus 3x plus x minus 1. And in fact, we find that there are, that's interesting, 2 places, but really the answer is x equals negative 1/3. And if you look up at this picture, I wonder how well we can see it in the light. I guess it's pretty good. If you look up at this picture of this blue line, negative 1/3 seems like a very good estimate for the x coordinate of this tangent line. At x equals 1/3, the slope of that tangent line is negative 1, which is parallel to this one. And we also found that the slope is that the derivative at x equals 1 is negative 1. That's just sort of a coincidence. What that shows is that this secant line actually is also a tangent line or something like that. But anyway, all right, that's all you had to do. And so maybe just to conclude, what is the significance of this x equals negative 1/3? The significance of this is that f prime of negative 1/3, the derivative of f at negative 1/3, is in fact negative 1. So it's at that moment that the rate at which the function is changing is the same as the overall rate of change for this function on this interval. Okay, 50 is maybe just another one of these, but now with some trig, yeah. Okay, let's go. So f of x equals 2 sine x plus sine 2x, and this is on the interval 0 pi. Okay, let's go. Same directions. Well, if you just plug in 0, you get sine of 0, and sine of 0 is 0. And if you just plug in pi, then you get, well, sine of pi is 0, and sine of 2 pi is also 0, so you just also get 0. And so this is, which is to say that in this case, f of pi minus f of 0 over pi minus 0 is just going to be 0 because they both have value 0. So really this is maybe a bad problem or something, because really this is the more of a Rolle's theorem kind of situation. They have the same y value at the beginning and end. Okay, whatever. We push on. When, if ever, does this function have derivative 0? Well, now we just take the derivative, and this is going to be the derivative of sine, so 2 cosine plus, what's the derivative of sine 2x? Well, it's cosine 2x back inside 2. So 2 cosine 2x. And now, well, the derivative is done, and so now the question becomes, when is that equal to 0? Because the mean value theorem says somewhere on the interval the derivative must be 0. Okay, so I just set this, I set this equal to 0, and now I just have a pre-calculus problem on my hands, which is not that hard, but not that easy either. Of course, I can divide by 2, and how does one go about doing this? Well, if you're experienced, then you know that the thing to do here is to apply the appropriate identity for cosine 2x, and the cosine 2x identity that I want is 2 cosine squared x minus 1, and that's good because now I have just a quadratic equation in cosine, and now I just hope that factors, and I guess it does. So that becomes 2 cosine x, 1 cosine x, 1, let's see if I did this right, 2 cosine squared minus 2, 2 cosine squared x minus, no, so I guess it should be plus 2 cosine x minus cosine x, and then minus 1. So there it is. So continuing, what do we find? We find that this happens at 2 places, when cosine x equals 1/2, and when cosine x equals -1. When is cosine x -1? At x equals pi, but that's like at the end point of the interval, so that's not what we want. When is cosine equal to 1/2? Here and here, but only one of those is on the interval 0 to pi. That's x equals pi over 3. And so the answer is that f prime of pi over 3 is 0, and that's the number on the interval 0 pi with a derivative of 0. Okay. Good. More. All right, 71 and 84, and these are both sort of theoretical, well, these are both kind of challenging problems. 71, well, let's just start. 71. What is 71? It says, use the intermediate value theorem and Rolle's theorem to prove that the particular equation given has exactly one real solution. Okay, and they give you an equation, x to the 5th plus x cubed plus x plus 1 equals 0. Okay, and the directions are, show that this equation has exactly one solution. So show this has exactly one solution. Alright, and alright, I did a problem almost exactly like this on the video, but I think the explanation was really bad because, well, instead of just kind of doing it, I asked all kinds of questions and my class was not answering me. So now I will just do it. How do I show that this is exactly one solution? Well, when someone says show that that there's exactly one of some mathematical object, as I said in the video, that's really two things. That's saying that there is at least one, and saying that there is at most one. And so the first thing to do is to prove existence. We shall confirm that this equation does have a solution at all. And how do we show that this equation has a solution? Well, we use the intermediate value theorem. And so let's define the function f to be the polynomial on the left-hand side of this equation. So x to the fifth plus x cubed plus x plus 1. And as we did back in the limits unit, we can now sort of search around for, or even back in pre-calc C we did this, for values which change this function slightly. So let's see, if I plug in 0 I get 1, but if I plug in negative 1 I get negative 2. So there we go. F of negative 1 is negative 1 and negative 1 and negative 1 is negative 3 and 1 is negative 2. So this is negative 2, but f of 0 is 1. And so, to make a sketch of this function, we see that here at negative 1, the value of this function is negative 2. But by the time I get to 0, we're already at 1. And so, somewhere on this interval from 0 to 1, this function has to cross the x-axis. Okay, it's been a while, so let's just remind yourselves how we write this. We say, okay, the intermediate value theorem says if you give me any y value in between the starting y value and the negative y value, then as long as this function is continuous, it must cross. Okay, and so of course f is a polynomial, so f is continuous everywhere, and in particular it's continuous on the interval negative 1, 0. And since it's continuous on the interval negative 1, 0, I can apply the intermediate value theorem. And if you give me some y value like 0 that happens to be between negative 2, which is the value of f at negative 1, and 1, which is the value of f at 0, then by the intermediate value theorem, there must exist a c on the interval negative 1, 0, such that f of c is 0. In other words, give me some y value, some intermediate y value, in this case 0, somewhere on this interval this function has to output 0. Okay, so all that proves is that since the function was negative and then later positive, that there must be a solution. Okay, so in other words, we have shown that a solution exists. This we could have done back before we knew derivatives, and even you could have just done this in pre-calc C, basically. Maybe without such fancy language like that the function is continuous, but the general idea of negative then positive later is kind of common sense. Okay, but now comes the other half of the proof, which is uniqueness. And to show uniqueness, what we have to do, remember the goal of the problem is to show that there's exactly one solution. So we have to show that we've shown that there is a